Hi, and welcome back for week 3. Last week we did kind of a review of basic electrical. Today we'll get to some of that, some practical applications, particularly of series circuits and voltage drop. But before that, we're going to do kind of a basic overview of computer systems. So let me bring up, let me turn me off here and bring up Blackboard. And we'll just pick 272 OB here. And I'll show you what I've added. Under lessons, there is now a second set of slides, and we're going to be working in those slides. So let me launch those. So week 3. Topics we're going to talk about. We're going to do an overview of electronic control systems in general. Then we go one by one and start talking about different types of sensors. We've got thermistors, potentiometers. So thermistors are temperature sensors used all over the car. We talked about those in lab a little bit this week. Potentiometers are typically position sensors of some sort, throttle position, accelerator pedal position, examples. Switches, everyone knows what a switch is. They're used all over as inputs. Some of them are operated, by the driver. Some are operated by pressure or some other system function. We have data streams. Those are going to be talked about in the input section, but they're also going to be talked about in the output section. AC generators, an example would be maybe a crankshaft position sensor or a wheel speed sensor. DC generators, the only example I can really think of would be an old-fashioned oxygen sensor, but we will talk about those. Pressure sensors and other sensors such as mass airflow, there aren't a lot of examples of the type of sensor that's a mass airflow sensor. So a lot of these other ones, thermistors, potentiometers, you find them all over the car. Something like a MAF, you only find in one place. Same with, for example, a wideband air-fuel ratio sensor. So let's start with the system overview. Every computer system, and the one I'm on right now is desktop. It has inputs such as a keyboard and a mouse. So inputs feed data into the computer. There's analog to digital conversion. So sometimes things are fed into a computer in a format that the computer cannot work with. For example, we saw in last week's lab, and we saw this week in the shop, a little bit about potentiometers and thermistors. And what we saw is that the voltage level coming out of those can vary, almost infinitely between 0 and 5 volts. So a computer can't handle an analog voltage like that. It needs to be converted into something the computer can deal with. Then we have processing. And the processing is kind of, I have it split into 3 different categories. There's a program, so the computer follows a program step by step. Calibration, which would be the numbers that it's using, almost like specifications. And then adaptive strategy is a term, I think that's a Ford term, but we're talking about things like adaptive idle speed control, fuel trim, where the computer can actually adapt a little bit to conditions. Then on the output side, sometimes outputs are analog. Well, not super often, but think about fan speed. That's a good example. We have an HVAC system. It has a blower motor. If that's electronically controlled, the computer is a digital device. The fan is kind of an analog device where more current flowing through it makes it spin faster. So we need some sort of circuitry to convert the computer's digital language into a varying, infinitely varying almost current, which is analog. And then, of course, there are outputs such as motors, lights and indicators. So here's kind of a diagram of the entire process. And notice that it kind of flows from left to right. So over here is data coming in from various sensors. The input interface, all right, so this is what I was talking about, when you've got maybe analog to digital conversion, maybe frequency to voltage conversion. So a sensor puts out a varying frequency. That has to be converted somehow. Basically, everything has to be converted into a number that the computer can work with. The microprocessor, so this is the processing portion of the whole procedure. But notice that it's reading and writing from different types of memory. So we'll talk about those in a minute, excuse me. And then after processing happens, you'd say maybe decisions are made, then there's circuitry connected to the outputs, such as solenoids or relays or lights, or LEDs or motors. So I guess I want to talk about how something might come in and be processed. So you've got an accelerator pedal position sensor, which is an analog sensor, possibly or probably a potentiometer. So it's going to have a variable voltage level coming in. As you step on that accelerator pedal, the voltage, maybe with your foot off of it, is 0.5 volt or 1 volt. The voltage pedal to the metal might be about 4.5 volts. And if the pedal's somewhere in between, the voltage is going to be somewhere in between. So in this, analog voltage comes in here, right? And it has to be converted into a number. So that number needs to be stored somewhere that can constantly be updated. So back when I first started teaching this class, students weren't very familiar with computers, but now I'd say that's probably not true. So you've all heard of RAM, random access memory. And RAM can be read from the microprocessor. The microprocessor can write to it. So it's a section of memory that is kind of like a scratch pad for the computer. Data in here is constantly updated, right? So if this accelerator pedal position sensor reading comes in and is put into RAM, the computer has access to it. It can read it whenever it wants to. So when it wants to update the position of the accelerator pedal, which will be frequently, it's going to run on a clock, right? So it's going to operate at however many megahertz and just walk through steps. And every so many steps, it's going to decide to update that sensor reading. Let me get rid of all of this scribbling here. So sitting here in RAM is our accelerator pedal position sensor voltage as a number. In ROM is going to be, and this is read-only memory, right? So this can't be changed. There's going to be a program that the computer's following where it basically goes through instructions, and when it gets to the instruction where it wants to check the accelerator pedal position, right? So it's reading the program out of here. It can then access that position from RAM. Now it has to compare it to something, right? So let's just look at like fault logic. Are we going to turn the check engine light on? In PROM, this is programmable read-only memory, there's going to be numbers that basically describe what an acceptable accelerator pedal position sensor reading might be. So what the computer can do, it has the accelerator pedal position reading already in here. It can look into the PROM and find out, okay, what's too high, what's too low, and it can make some sort of a comparison. And I'm going to go through this in a little bit, kind of give you an example of a computer system doing that, making a comparison. And then based on that comparison, if it's just, we're just talking about the fault logic here, then it can send out into this input interface a number. And if that number is 0, the light stays out. If that number is 1, the light goes on. So based on a reading that came in here, following directions that came from here, this microprocessor can access the reading that came in this way, right? It can compare it right here to acceptable readings that are stored in PROM, and then based on the comparison, it can send out the result. So it's kind of a flow through here. So if in this system, right, if this were a desktop PC, you know, here would be keyboard and mouse input, right? This here might be the program that's running, whatever particular application is running, whether it's Word or Excel or whatever. So these are going to be the instructions that the computer's following. This would be the data maybe that you're typing in or that it's reading. And what would be the outputs on a desktop computer? You'd have the monitor. You might have speakers. In the classroom, we have a projector on the ceiling. Or you might have a network. Might be sending data out the network. So if you're running email or something like that, the output is not so much the screen, it's a network, the other computer. If you're reading email or if you're watching, you know, if you're viewing something on the web, then that data in is coming in from the network instead of some sort of a sensor or a keyboard or a mouse. So let's move on to the next slide here. Just kind of go through this a little bit more. So input. A series of sensors provide the computer with information in the form of, could be varying voltage, so this is an analog voltage. Could be a varying frequency. So some mass airflow sensors, for example, old style Ford manifold absolute pressure sensors, the frequency coming off of those changes, the voltage remains pretty constant. It's just flipping on and off at a different frequency. Straight up on and off inputs. So voltage is there or voltage is not there. Switches, like a good example of that might be your brake light switch. The computer might see no voltage on that circuit, and then all of a sudden it changes from no voltage to some voltage. It knows that the driver has stepped on the brakes. And there are things it might do. It might disengage the cruise control. It might unlock the torque converter clutch, because we don't want that on when the brakes are on. Or when you're first starting the car, it might allow the starter, knowing that you have your foot on the brake. That's a really simple input. Then we have data streams coming in from other modules. An example, we talked about this in one of the labs. Somebody was asking about the speedometer and speed sensors and things. And the vehicle speed sensor, probably on most cars, feeds into the powertrain control module. And then the instrument cluster with the speedometer in it gets its data, its vehicle speed data, from the powertrain control module instead of having its own sensor. So inputs definitely can be data streams. Analog to digital conversion. Computers don't understand infinite voltage differences. They only understand two things. And you might ask, okay, well, computers have to deal with much bigger numbers than 0 or 1. And this is it's a little bit of a strange concept to get used to, but usually in the classroom, I do this on the board, and it's a little easier to do. It's a little more difficult to do on the recording here. But every number can be represented by a series of ones and zeros. Give you an example. Let's see if I can, if I can shrink this down a minute and bring up the calculator. Okay. So notice it says standard. I am going to switch it to programmer. Okay. And let me type in the number, say 50. All right. 50. If we look over here, we'll notice that something called binary bin here. And it shows just a bunch of ones and zeros. Notice there are, if you look over here, let me see if I can highlight that a little bit. It kind of blocks things. But there are a series of 8 zeros or ones. So this would be 8 bits, and it would be called a byte. We go back to decimal here. If I change that 50 to, let's see if I can clear it here. How the heck am I supposed to clear it? No, don't have to clear it. Let's see, we start with 50. Here's what our 50 looks like, right? 1, 0. Let's start with 0. What does 0 look like? Just a 0. If we go back to 1, where's our 1, right? Notice that the very first digit has changed to a 1. If I go to 2, we have 1, 0. If I go to 3, it's 1, 1. If I go to 4, it looks like a 100. So what's happening? Let me go back to the PowerPoint here. See if I can actually draw this. All right. All right. I'm going to try to draw this. With one digit, 1 bit, I have 2 possible numbers I can have. I can have a 0 or I can have a 1. That's all I get. 2 possibilities. Right? If I have 2 digits, I can have 0, right? I can have 1. I can have 2, or I can have 3. So I have 4 possibilities, right? 0, 1, 2, 3. If I decide to go out to a 3rd digit, I can have 0. I can have 1. I can have 2. Okay. I can have 3. So far, notice it's exactly the same as these, 0, 0, 0, 1, 1, 0, 1, 1, right here, except for there's a 3rd digit, but in this case, they're all zeros. If I start over again with a 1, right, 1, 0, 0, 0, equals 4. I'm sorry, 1, 0, 0 equals 4. 1, 0, 1, right, equals 5. 1, 1, 0 equals 6, or 1, 1, 1 equals 7. Now I have 8 possibilities, right? Here I had 4. I had 0, 1, 2, 3. Now I have 0, 1, 2, 3, and then all over again, 4, 5, 6, 7. So I'm able to get 8 possibilities. In computers, if we use 8 digits, right? 8 bits, we call that a byte. We start with, 1, 2, 3, 4, 5, 6, 7, 8 equals 0, right? And then way down here, if we're all ones, that equals 255. So with 8 digits, 8 bits, or a byte, we can have from 0 to 255, we can have 256 different values. And so what's going to happen, let me get rid of all these, is as these voltage levels come in, we see it from 0 to 5 volts. The computer is going to see it somewhere between 8 zeros or 8 ones. Let's say the computer wants to store the number 142. It's going to look like this. And let's see. Got to click on that again. Again, if it wanted to store the number 0, it would be all zeros. If it wanted to store the number 255, it would be all ones. So when we're looking at a scan tool, we're seeing a voltage number, or we're seeing a temperature or a percent. What the computer is actually seeing is just numbers. But for us, so that it makes sense to us on the scan tool, these are converted into a value that that's proportional to the number. So now the processing phase, right? Actually, you know what? Let me go back because I have something else to look at. We'll close down this calculator. Just give me a minute here. All right, what you're looking at, let's see if I can expand this at all. Yeah, probably not. Okay, I'm just going to look at decimal, this column here. And this column, and this column. Let's just try to put this all together. When I hit, say, a lowercase j on my keyboard, so here's lowercase j. I see a lowercase j. What goes down that wire from the keyboard into the computer is not the letter J. It's not floating through the wires as a letter. What the computer sees, right here, is a number 106. But let me get rid of the pointer here. That 106 doesn't look the same way that it does to you or me, right? We know what that 106 looks like to the computer. It looks like a series of ones and zeros. Now, what's a 1 and 0? That's either voltage or not voltage. So remember, these are electrical signals. And so when you hit that lowercase j on the keyboard, what goes down the wire are pulses of electricity, zeros and ones. If, on the other hand, I hit, say, an uppercase C, notice that is, looks like 67. 67 to the computer. Looks like 67. Looks like that. So that's what's going to go down the wire. So it's not seeing letters, numbers. In fact, for every single character that you can type on a keyboard, including backspace, spacebar, there is, here, spacebar, if you look, is going to be a 32. There is some sort of number associated with that character. And of course, the computer sees that number as a series of electrical pulses. So I know this all seems a little bit strange, but let me bring this back up to full speed here. Just to understand that everything the computer sees is actually electricity, right? It's not actual numbers, it's not actual letters. So somehow things have to be converted from voltage levels that are, analog into something the computer can work with and store just with ons and offs. The computer basically stores things in a bunch of on-off switches. That's what memory is. Billions and billions of little on-off switches. So to store this number 142, it's going to store it in a set of switches that are on and off like this. Are they real switches? No, obviously not. They are, electronic, but nonetheless, that's how it's got to store it. So let's talk a little bit about what happens in the processing portion of this whole computer system. The computer is following a set of instructions. So I say here, if, then, else. Here's what I'm talking about. A programmer has written a program that the computer's following, and it's going to be checking things. So let's say we're looking at the intake air temperature sensor. The computer wants to look at the intake air temperature sensor, and I'm just going to stick with the error logic, right? How they decide whether to turn the check engine light on or not. So it might read something like this. It might say, if the intake air temperature is, is less than negative 40, right? If you remember from the lab, when we pull the plug on there, it goes to negative 40, right? Get rid of that. So if the intake air temperature is less than, say, negative 39, then I'll go here. Then turn on the check engine light. Else, turn it off or leave it off, right? And there can be multiple things, right? So it could say instead, get rid of this, do it again. We know from the lab that, when we pulled the electrical connector off that intake air temperature sensor on some of the vehicles, and on a lot of vehicles this happens, we're looking at the scan tool, it reads negative 40. When we shorted the wires together, it read like 248 degrees. Neither of those obviously would be a normal intake air temperature reading. So the logic for determining whether to turn the light on in the computer might look more like this, right? If the intake air temperature is less than negative 39, right? Or if the intake air temperature sensor is greater than, 247, then turn on the light. Whoops. else continue, right? Go on and do something with that reading. So this is just a simple kind of checking different conditions. And if we go back, let me get rid of this. If we go back to this system overview, I'll find it. You know, that program, right, is stored here and is being pulled into the microprocessor. It's reading those, you know, if this, do that sort of things, right? And so it's reading that sensor reading out of here, and that -40 or -39 or +247, that might be read out of here. Maybe able to talk about that a little bit later. So calibration, let me talk about what calibration is. Because you can have the same program running on two different cars and have slightly different results. Maybe one car has a trailer tow package and the other doesn't, so they calibrate things a little bit different. You can have a program, right? So I'm going to do this, let me try to write it out. Like I say, this is tough in a video because I usually am talking to you and doing this on the board, but let's say you're reading a shop manual and the instructions, right? You're changing a tire, or you're torquing down a cylinder head, and so what it tells you, you know, it could tell you this. It could say tighten, you know, the head bolts to 110, you know, pound-feet, foot-pounds, right? And these instructions would be good only for that particular engine, right? Another way to do it would be to say, tighten the head bolts to specification. And then somewhere else, the specification would say, head bolt torque is 110 pound-feet, foot-pounds, right? Now, what's the difference between these two things? You can follow either set of directions, and the head bolts would be tightened to 110 foot-pounds. The difference is, on the first one, this instruction is only good, it's kind of hardwired into the process. In the second one, you can have the same process, the same program, if you will, the same steps, but you can change the torque setting and kind of reuse the process, reuse the instructions for different vehicles that have different size head bolts, let's say. Same exact process, different number. Now, I know that doesn't seem to make a whole lot of sense when it comes to a computer, but I think I can show you in a little demonstration in a few minutes how that, you know, would work in real life. Then we have something, one term is adaptive strategy. The most common example of this is fuel trim. You know, sometimes they call it long-term adapt or short-term adapt. We've all heard of fuel trim. We dealt with it last semester. It's essentially where the computer is able to kind of learn and adapt. You create a small vacuum leak. The computer realizes the new normal is that it has to add a little bit of extra fuel to make up for that extra air. And so it calibrates itself to that new requirement. We'll talk a lot about that later. And on the output side, we've got digital to analog conversion, and that might be something like the brightness of a light or the speed of a fan or something. I talked about that. Computers talk digital, and not everything on the outside works digitally. Think about your, you know, your volume on your computer speakers, right? Computers, obviously, everything is digital. Volume is definitely a sort of an analog thing. And then, of course, we have outputs. Devices inside the computer switch circuits on and off. Or they regulate voltage, or they regulate current. They can regulate current through pulse width modulation, which we'll talk about when we get to outputs. Outputs, solenoids, motors, lamps, devices which are controlled by the computers. Another type of output could be that data stream. So we talked about on the input side, the data stream going across the network. On the output side, we have the same thing. So the output from one computer can definitely be the input from another, input to another. Okay, before we get into the actual, inputs, thermistors, potentiometers, switches, data streams, let's look a little bit more at this processing. So I'm gonna see. I have here a blank Excel spreadsheet, and Excel has the capability to do a little bit of computing, if you will. So let's see how the logic might be for determining whether to turn on the check engine light when it looks at the intake air temperature sensor reading. We know from the lab that the intake air temperature sensor, when unplugged on a lot of cars, goes to -40. So we're going to use that number. And when the wires are shorted together, it goes to +248. So we'll use that number in this little example. So we'll have the intake air temperature reading. I'll put that down here. So let me just name this cell IAT. All right. And in it, I'll put, 100 degrees for now. So that's good. Here, let's basically put our check engine light, right? Is there a fault? Let's make our reading, we'll make our reading blue. It's hard to see. We'll make our fault, we'll make that yellow, right? So, how do I make this work? Little computer logic, right? If our IAT is, let's say, less than -39, right? We know -40 is what's going to happen. That's going to be true, and if not, it'll be false. All right, so right now it says false, right? So here's what our computer is doing. It's comparing a reading, IAT, that's sitting right here, right, to a number, -39. So if we go back to thinking about our calibration, we can change this again, right? Instead of 39, right? Let's name something here. Let's say we'll call it the IAT low limit. Let me name it that, right? IAT low, right? And I'll make that -39. Right? Now I can rewrite this. Oops, I screwed that up. IAT low is -39. I can rewrite this to say if it's less than IAT low, right? Which is now -39, right? So if our IAT right here 100 is less than our IAT low limit, which is negative 39, then our light does not come on. So here it's 100. Let's make it negative 40. What happens? Bam, our light comes on because we're now lower than that low limit, which is negative 39. Let's change this low limit to negative 50. Oh, light goes out. So on one car, this low limit might be negative 30. Got that wrong, negative 30. Right? We're at negative 40, light comes on. On another car, maybe it's negative 50. Negative 40 reading is not going to have the light come on. So the computer is running the program here, looking at the reading here, and then looking at a spec here. So let's put this back to negative 39. At negative 40, our light's on. At, say, 100 degrees or 110 degrees, our light's going to be off. Let's add some more into it. Let's put a high limit in. That's what we're going to call this, right? IAT high. And we'll make that 247 degrees. That's what we saw in the shop. So we can write this again. We'll check both. Now we're saying if either of these is true, if we're less than our IAT low limit, or if we're greater than our high limit, right, we're going to have a problem. So right now we're between the negative 39 and the 247. If we go down to negative 40, our light pops on. If we're at 200, it's off. If we go above this 247, let's see what happens. The light pops on again. So this is just an example of what's going on there. It's not thinking, it's not making decisions, it's just making comparisons, right? A programmer, an engineer has decided if we're below negative 39 or above 247, right, those are the limits, then our light's going to come on. We have a fault. If we're in between, our light's going to be off and no problem. Now let's go with one more example. So the computer can also make sure that multiple conditions are met. Think about this. You go to start your car. Nowadays, you have to step on the brake pedal and press the start button. How would a computer handle that? So let's look at, we'll say this is the brake pedal, right? I'll rename this brake. And we'll say this, we're going to call start button. Okay, and we'll rename that start. And we'll say right now we're not doing either one, so it's false, that's false. Now the question is, do we start the vehicle? So here's what it's going to be. We're going to use and. What did we call this again? We called this no, we didn't call it anything. We call it something here. Call that brake. Call that start. Okay. And brake. Start. All right. Vehicle's not going to start. If we step on the brake, right? Vehicle still doesn't start. I think I can just do 0 here, right? 0. And here, if that's 0, we step on the brake. Nope. If we push the start button, nope. But if we step on the brake and push the start button, the vehicle is going to start. So the computer can look at, one thing. It can compare numbers to what a programmer or an engineer has put in. It can make sure multiple conditions are met. And then this is the output, right? Do we send voltage to that starter relay? In this case, we do. If we haven't stepped on the brake pedal, though, we do not. All right, let me stop sharing this stuff here and start the video back up. Just talk to you for a minute. So I know a lot of this stuff might be confusing, and you're not writing software that motor vehicles are operating off of. So do you have to actually know this, cold? No, you do not, right? It's just kind of my idea to give you an overview of how these things work. Computers don't really think, there's not a little brain in there. What they do is they take in inputs, they compare them to, values they have stored somewhere in their memory, and then, if things compare favorably, something happens. If they don't, it doesn't happen. So you saw the logic of how it may choose to turn on a check engine light if some sort of sensor reading. We used IAT, but it could be anything else. If it falls outside a range that the programmer has determined is normal, then that light comes on and a fault is flagged or a fault is stored. We saw how the computer can make decisions, sort of, right, like the one about whether or not to start the car, only if both things are true. If you have stepped on the brake pedal and if you've pushed the start button. One or the other doesn't do it. You have to have both. So one last thing, we'll start talking about thermistors a little bit. This is something, if you're watching this and you're in the Thursday night class and you're watching it Thursday afternoon, we haven't done it yet, but everybody else, we looked at thermistors in the shop. We looked at one on the bench and we looked at several in the cars. So I just want to bring that up and look at that a little bit, and then that'll do it for today. So let's see. Give me a minute. I'll close this. Nah, we don't need to save that, right? Somewhere up here I have, if I can get rid of this. There we go. I have a schematic. This is from General Motors vehicle. I don't remember exactly which one I pulled up, but thermistors are the first sensors we're talking about. And so I'm showing one here on a wiring diagram. It's the engine coolant temperature sensor. Up here is a fixed resistor. Notice it's inside the engine control module. Right here is showing a source of voltage. So what you have here, right, if you follow this all the way down, start to finish, this circuit is you have a series circuit. You have this resistor, which is fixed. It's probably, say 30,000 ohms or something like that, 33 possibly. You have this resistor out here, thermistor, so you see that line drawn through it like that indicates it's a variable resistor. And a thermistor, just you can tell by the term, thermal, right? It's a resistor which changes resistance with temperature. And we saw that in the shop. We took a thermistor and we warmed it up and we measured the resistance and we saw what happened. And then we looked at it on the car and saw what happened as the engine warmed up. So what's happening is, if we have a series circuit, going back to your basic electrical, and you have two identical resistors, right? So if this one and this one are identical, if they're both, say, 33 k ohms, then the voltage drop on each of them will be identical. So if I give this 5 volts here, then at this point right here, I'm going to have 2.5, because this resistor here and this resistor here will drop identical amounts. They'll each drop half of it. If this resistance out here changes, right, because this one inside is never going to change, but this one here, it will change with temperature. So as we get warmer, this is a negative temperature coefficient, so as we get warmer, that means the resistance is going to decrease. If the resistance decreases on this one, its voltage drop will decrease. And the voltage drop of this one will increase. It has to, because together they drop all 5 volts. So if this drops less, then this one has to drop more. So if they are identical, and this is reading 2.5 volts right here, and all of a sudden this one starts dropping less, this is dropping more, this voltage level here is going to go down. And so most of you so far have seen that in the shop, but that's how these circuits work. Using the voltage drop on this series circuit, fixed resistor never changes, but its voltage drop is affected by what's going on out here. And the voltage measured here is affected by what's going on out here. So hopefully that didn't confuse you too much, the whole thing. Lab is a perfect time to ask me about this stuff, because a lot of it is hard to explain when you don't get to ask any questions. So I tried to put it out there where you can see it. One thing I do like about these videos is you can pause them, back them up, watch them again if it didn't make sense the first time. What I don't like is that you can't ask any questions real time. So please, in the labs, feel free to ask questions, bring this stuff up. I'll draw it out. We'll get some parts, we'll hook up power, we'll make it happen in the shop so until it makes sense to you. So that's about it until next week. I try to do these every Thursday, so we'll see you next Thursday, I guess, and I'll see you in the shop.